We sort of are hopefully finish up chapter 3. Maybe not today, but next time. I'm going to send y'all some extra problems in case you want some extra problems. I think if you do the homework and do the problems that we do in class and look at the old test, you should be okay. But just in case you want to do a little extra, that's fine. And I'll send some out, 3 or 4 extra problems, kind of like with chapter 2. There is an exam coming up, as you know. Let's see, it's, what did it say? Next, not this Friday? No, when is it? The 30th? So that's 2 weeks from Wednesday? Yeah, so just sort of looking forward to that. We'll definitely have all of chapter 3. Yeah, right? What's the date of that exam? The 30th? It's on the back of your book, actually. So, yeah, it's Wednesday, September 30th. And we'll definitely have all of chapter 3 on there, all of chapter 4. We might even have a little bit of chapter 5. Chapter 5 is on work and energy, so we might go and introduce dot products and stuff. But if you're in Calc 3, you've already had dot products, right? Dot products? Dot products are super easy. It is Calc 3, but like I said, it's super easy. So even if you're just in Calc 1, don't sweat it. I'll give you everything that you need to know about it. Um, it probably is the hardest test of the whole semester, so please make sure that you're preparing now. Because students generally do find the second test to be the hardest. Chapter 4 is difficult. Chapter 3, students sometimes find difficult. Chapter 5 is easy, but Chapter 4 will be probably the most problematic chapter of the whole semester. Okay? So just a little warning about that. Make sure you're spending a lot of time now so that you're not overwhelmed the week before the exam. Let's see. Sort of started introducing projectile motion. Uh, Remember, it's characterized by these accelerations, that we have 0 acceleration in the x direction, that we have an acceleration of 10 meters per second squared in the y direction, and then we just treat those two problems completely separately. We treat the problem of the object, going up in the air and then coming back down again, and then we treat the problem of the object traveling along the x-axis with a constant velocity. Let's see, did I give you sort of the equations as they fall out? I don't think that I did. Let me go ahead and give those to you. Let's see. Did we look at this, the video with the guy? Okay. Did I do the thing with the basketball? Right. The logger pro bit? Yeah. So let me just sort of sketch out those equations as you see them. Remember, in kinematics, we just have the 2 equations. By the way, if you look in some other physics textbooks, you'll often find a third and maybe even a 4th equation, like a v squared, v naught squared, 2ax kind of thing. They just get those equations by substituting one equation into another. If you want to use those, that's fine. But I find that it's often easier just to remember the 2 kinematics equations that we have. And then when needed, you can substitute one into the other. So anyway, these were the 2 equations. We had the v equals v naught plus at, and then x equals v naught t plus 1/2 at squared. We've seen those already. And then we can break those into, for projectile motion, the y component. And in the y direction, we just write them exactly the same. Vy equals v naught y plus ay times t, right? These are just saying these equations hold true now for the y component. And then y is equal to v naught y times t, 1/2 ayt squared. And then we can write those same equations for the x component, but they become a lot simpler because it's just a lot simpler problem. When we're dealing in the x direction when there's no acceleration, we can write them now as vx equals v naught x, because this term goes away since ax equals 0. And we can also write it as x equals v naught x times t. This term goes away because ax is equal to 0. All right, this doesn't really mean anything. That just means that the velocity in the x direction is unchanging, that the velocity at any point in time is equal to that initial velocity. So this, you wouldn't really use this in a particular problem, except for the fact that you know that the velocity is not changing. And then, of course, this is just our basic understanding of position, velocity, and time. We could rewrite this, in fact, not with the initial velocity, but just x is equal to vx times t, right? Because we know that those two are equal. So if you're into memorizing equations, like, really no need to memorize these except that we remember these two equations and then remember that they apply in both the x and the y direction. Let's work through some problems. Um, let's see. Let's work just sort of the basic prototypical uh, kinematics problem or projectile motion problem. That's when you have an object that goes like this and it returns back to the same location. Listen, every projectile motion problem is a little bit different, but almost always you're going to have to find the time in a certain way. What determines the time that an object is in the air? What determines the time that an object is in the air? I don't think we said this explicitly, but you might be able to figure it out. Determines the time that an object is in the air. Okay, the gravitational acceleration, that does have something to do with it, but that's going to be always the same for everything that we're dealing with. What's that? Okay, the angle does affect it, right? But that affects something bigger, Brandon. The initial velocity affects how long it's in the air, all right? Those things are all true, but I want you to think more basic in that the height that the object travels determines how long it's in the air. So if I throw this thing up like this, it's in the air a certain amount of time. If I throw it up like this, it's in the air a longer amount of time. So, oh shoot. The y motion, we'll always use the y motion, almost always use the y motion to determine how long an object is in the air. So that problem that we worked earlier in chapter 2, where an object goes up, it comes to a stop, and then comes back down again, we'll use that same method. Remember where we said that the velocity at the top is 0. We can find the time for half the trajectory, and then we can find the total time. We'll use that same method to work projectile motion problems in order to find the time that that the object is in the air. So let me just sort of sketch that the time an object is in flight. I'm going to call this sort of the hang time. Right? How long is it in flight? That this is always dictated by the y motion. So if an object goes up higher, it's in the air for longer. If it goes up lower, it's in the air for a shorter amount of time. And then we can remember some things about this motion here. We know that Vy top up here is equal to 0, and the time required to go up is equal to the time required to go down. And that's just sort of harkening back to our one-dimensional problem that we worked before, where we have an object that goes up and comes back down again. And forgetting completely about the x motion. That's a completely different thing. Let's see, well, let's watch this clip. Have you ever seen this movie, Gone in 60 Seconds? Nicolas Cage? It's getting a little dated. Have y'all seen it? Who hasn't? Raise your hand if you've seen it. You haven't seen this movie? Okay, it has Nicolas Cage. Nicolas Cage, his brother was kidnapped, and he has to go out and steal like a bunch of cars, and then his final car was like this really sweet Mustang Shelby GT or whatever, and in the end he's running from the police. They're trying to catch him, and he comes to a traffic jam on the bridge. Oh no, what's he gonna do? What does he do? He jumps over it, right? There's a tow truck there with a ramp that was conveniently placed for him to go, and he jumps over it, and he follows a path that's very much like this. Right? I like this clip because it tells us a lot about his motion, and it gives everything that we need really in order to solve how high does he go, right? What is his range, and then we can also find his velocity at particular points. So let's just watch the clip. As you're watching, I want you to think about what is the information that we need in order to find his range and his maximum height. So I'm looking both for this distance, x, and I'm also looking for this distance, y, in order to determine the range and the maximum vertical height. What are those two pieces of information we need? What's the first thing we need? We need to know his speed, right? How fast was he going? Could y'all catch right before he hit the ramp? What was his speed? Right, it was right at 100. So we'll just say he's going 100 miles an hour. So we need his speed. And remember, this is neither the x nor the y component. This is just his initial speed. His initial speed, v naught, was about 100 miles an hour. Of course, we need to convert that to SI units. So in 1 hour, 3,600 seconds. 1 mile is 1,609 meters. And that gives us 45 meters per second. So if you're going about 100 miles an hour, it's about 45 meters per second. In 1 second, you cover about 45 meters. It's nice to be able to sort of go back and forth because I say your friends will be impressed if you're going 100 miles an hour and you look over at them and say, hey, I'm going 45 meters per second. And then they'll think that you're really cool because you are, right? All right, so that's our initial speed. There's something else that we need. What else is it that we need? We're going to find the time, Cody. Yeah, so we will need to find the time. But in order to do that, what do we need to have? We're going to find the distance, yeah. Somebody said the angle of the ramp. And we know the acceleration. When he goes in, when he hits the ramp, his acceleration in the x direction is now 0, and his acceleration in the y direction is -10 after he leaves the ramp when he's in motion. But we need to know the angle, right? What angle do you think is that ramp at? Y'all think 45? Maybe 45. 45 is a dang steep incline. That's like that. Like if you were on a 45-degree incline, it would be almost like you were climbing it would feel like you were climbing a hill. But let's say it's 45. I think it's probably a little less than 45. But 45 would be a nice angle. Why? Because it gives us what? Max range. So you would presume that, the people doing this stunt, that they would want to get the maximum range. So let's say 45 degrees, because this gives us max range. But it's probably less than that. So we'll just sort of remember that it's probably more like 35 to 40 degrees. But let's just take it at 45. We need to calculate the components of the initial velocity. So remember, we need to do v naught x is v naught cosine of theta. That's going to be 100, or excuse me, I'm sorry, 45 meters per second times cosine of 45. It's 0.71 times 45 is 32 meters per second. And then your velocity in your y direction, v naught y, is going to be the same just because cosine and sine of 45 are the same. All right, so remember our velocity now, it was like this. This was our v naught. But now we're breaking it into our two separate components. So now we have our v naught x and our v naught y. All right, now we're just going to treat each problem completely separate. Our first job will be to find the time that it's in the air. And in order to do that, we're working that problem like we did in chapter 2, where a thing goes up and then comes back down. So we know that at the top of the trajectory, just working solely this problem where it goes up, comes back down again, we know that the velocity at the top is equal to 0. Right? And then I can say then that v top equals v naught plus at. I'm going to add our little subscripts though now, just so I'm clear that I'm talking only about the y motion here and not about the x motion. Remember, by the way, if I plot this y versus t, it looks like this. That describes just the up and the down motion. Big positive velocity, smaller positive velocity, zero velocity, increasing negative velocity. So that just describes our y motion. It does nothing to do with the horizontal motion. All right, so I get 0 equals 32 plus -10 times t. I'm going to call this t top because that's the time when it's right up here. If I solve that for t top, I get 3.2 seconds. I can do the algebra there. You just take the 32 over, it becomes -32 equals -10 t. Divide both sides by -10. All right, so that tells me the time at the top of the trajectory. If I want to find the range, what time do I need to use? I have to double it, right? Because remember that same problem, finding this time to get from here to here is just half the total time, only because I'm beginning and ending at the same point. Now, we will have some problems later where you're not beginning and ending at the same point, and you have to approach those problems a little bit differently, but the same ideas still hold. So this is our t top. So our total time then is going to be 6.4 seconds. So the total time in the air is 6.4 seconds. That's twice t top. If you look at the video, actually, this compares with about 7 seconds from the timer on the clip. So it's a little bit lower time. What would give you less time in the air? What could we change to give us less time in the air? A couple things we could change. The angle we could change, or the speed. Right, so if we change the angle or the speed, lower either one of those, it would give us less time in the air. All right, next we're going to find the range. This is pretty simple. Remember that x is equal to vx times t. What was that? 32 meters per second times t, which is, gosh, which one do I use? Do I use the 6.4 or the 3.2? I'm going to use the 6.4 seconds. And so that's about almost 200 meters. What is it? Was it 205? Or we'll call that 210 meters. I think that's pretty far. Like 200 meters is pretty far. But again, we probably miscalculated that angle or assumed a higher angle than it should have been. So his actual distance would have been a little bit shorter than this. I think it's actually pretty legitimate. Like as far as a stunt goes, it's one of the better stunts on TV. Getting it right. 200 meters, about 2 football fields. You think he went about that far? No, you don't think so. Not sure. Okay. Well, I also want to find, well, let's not just find his range, his horizontal range. Let's also find his vertical range. All right, that is, what is this distance, y? And I can say then that y is equal to v naught y times t plus 1/2 a t squared. Listen, a couple things that you need to be careful about. It was easy on this problem because the components were exactly the same, but usually on problems you won't have the same components because you'll have an angle that's not 45 degrees. You need to be careful that you use the appropriate values when you're doing these x and y components, because often students will mess those up. I always do that sort of the very first step is I find my x and my y components and I put them up at the top of the problem, and then when I need those values, I know what they are. Uh, so if I want to find y, v naught y was 32 meters per second. And then another problem that students make is they don't know which time to use. Remember, these are just functions, right? And so if I want to find the position at a particular time, I can just put in that time. So if I want to know the position here, then I know the time at that point in space is equal to t top, which we found to be 3.2 seconds. So I'm just going to put in my t top, or 3.2 seconds, 1/2 -10, because this is a y, times 3.2 squared. Anybody, Beans, do you have that? Or anybody calculate that? I don't have it. Okay. It should be about 90 minus about 40-ish, 45-ish meters or so, I think. How many? Okay, 51 meters. So he goes about 51 meters. That's the distance from the ground up to the maximum height. I think that's a little high. But again, if he had a lower angle, he would go considerably lower than that. Okay, what is his speed at impact? Listen, you should be able to tell me his speed at impact right off. What is his speed at impact? What is it? No, not 32. Somebody said it, I think, over here. It's going to be 100 miles an hour, right? Whatever his speed at the beginning is going to be the speed at the end, right? Assuming that there's no forces acting on him. So we can say his speed at impact is 100 miles an hour, or, 45 meters per second. I think it's useful just to sort of step through this and work through the vectors. So let's just do this sort of as a little exercise that if I want to know, I can plot out his trajectory, something like this. Uh, I know that I have a y component here, Vy, and an x component here, Vx. And then I have a y component over here, Vy, and my x component, Vx. These are the initial components, V naught x, V naught y. I can calculate what both of these are. I know that Vx is unchanging, that Vx is equal to V naught x, and that's equal then to 32 meters per second. So that's the magnitude of this vector. And then I can also find the magnitude of this vector, Vy is equal to V naught y minus AY times t. That's going to be 32 minus 10 times 6.4. And as we'd expect, it has the same magnitude as the original vector, but it's in the negative direction. This is negative 32 meters per second. Well, you should know that without really working it out. You should just be able to look at it and tell that that velocity in the y direction is negative and has the same magnitude as the original initial velocity. But it might become useful knowing that you can do this just to find the velocity at particular points in time. So what if I asked instead, for example, what is the velocity at this point? And then you could determine the velocity at that point if you know the time at that point, just by going through the same procedure. We'll see some problems like this in just a little bit, maybe next time. All right, so, and then if I want to find the net velocity, I have Vx in this direction, I have Vy in this direction, and it just becomes a vector problem, and I want to find V. So V is going to equal to the square root of 32 squared plus negative 32 squared. I don't need to do that because I know that it has to be 45 meters per second. But you might have to do that procedure if you were finding the velocity at another time, at a particular time in space, which we'll see some problems like that in just a bit. All right, this is sort of a typical projectile motion problem. I would expect on your test to not have one exactly like this, but you'll have one that's slightly more complicated, and we'll work through some examples, but this is sort of a good beginning point on how you solve these projectile motion problems. I feel okay with this? It's really just kinematics, but if you didn't really get kinematics in Chapter 2, it's going to sort of come back to bite you. So if you're having trouble with Chapter 2, then by all means come see me and we'll work through that together so that you can do well on the Chapter 3 problems. But the good news is if you got Chapter 2, hopefully this is going to be pretty easy for you. You're just throwing in vectors now. All right, let's see. I think I have another problem here. I want y'all to try this. So this is the same problem, basically. It's very similar, rather. Oh, no, this is a different problem. But let's try this. Let me pull up my clickers. Y'all go ahead and start. This is... Here you're looking for V naught. I just want to remind you uh, that V, um, V naught x is equal to V naught cosine theta, and V naught y is equal to V naught sine theta. You might want to write out your equations and sort of think about what are my knowns, my unknowns, and then as you're doing that, you might want to go ahead and plug these things into there, because really what it is that you're looking for is this V naught. So you want to find some way to isolate that variable so that you can predict what is, or so that you can determine what is that initial velocity. I'm just going to write the equations over here on the side. You shouldn't really want to have to do this every time, but since this is all sort of new right now, I'm going to do it. Right, we're sort of all over the board. I'm going to give you a little guidance here because most of you are sort of all over the board with your answer. So I know some things here that I haven't written. I know that AY is equal to -10 meters per second squared. I know that Vy at the top is equal to 0, and that's really all the information I know about the velocity. And I also know that this occurs at a time of 0.5 seconds. So this is sort of a fixed point where I know both the time and the velocity in the y direction. I don't know the initial velocity, but I do know that the angle is equal to 30 degrees. So in this way, it's a little bit different from the first problem that we worked, where I don't know the initial velocity now. Think about, of these functions that I have that describe these particular things, what are my knowns and my unknowns? And then is there one actually that I just have only one unknown in that equation? If there is, then it's really easy to solve. If there's not, then I might have to solve a system of equations to do so. I'm going to mark my unknowns in blue. That's unknown. That's unknown. That's unknown. Let's see, I don't know why. I don't know that. Do I? I don't know that. I know this if it's at the top, right? But I don't know that. That's it. And I know this if it's at the top. All right, folks, we'll just go about 15 more seconds. If you're not sure, you just go ahead and guess. I'm going to stop at 5:20. 5:20. Okay, yeah, we're all over the board. Slightly more of you got D. D is the right answer. Really, solving these, this will come with time as you get a little bit more comfortable with projectile motion problems. You get sort of comfortable with the functions that you're using and the ones that you're trying to solve. But this one is a little bit different because it's sort of different things that you don't know. But it's also pretty straightforward because it's just a simple equation, just solving a single equation, because I can take this one and I know everything but V naught. So I can say 0, that's my Vy at the top, is equal to V naught sine of 30. That's my angle, minus 10 times T top. And I want to put 0.5 seconds there because I know that at the top, that's my time. Because it required 1 second to go the full trajectory, it just requires a half a second to get to the top. And then I can solve this for V naught. And it works out to be 5 over a half, 5 over sine of 30, which is equal to 10. All right, so D is the right answer. Let's try this next one. Well, y'all going to do this in lab this week, I think, actually. Yeah, y'all do this in lab this week where you shoot a spring-loaded gun, and you have to measure how far it goes, and you can determine the time that it travels and what have you. So here, the displacement is 1 meter. The initial speed is 5 meters per second. Notice that it's fired horizontally, so that tells you something about V naught y and V naught x. You need to think about what that is that it tells you about those two velocities. And we want to determine how far does it travel in the x direction. Your first job would be to find the time in flight. Remember, when you're finding time, you almost always use what motion, the x or the y motion? You almost always use the y motion. So to find the time in flight, you'll use the y motion. And then in part 2, you just want to find the range, which is actually what it's asking for. And anytime we're looking for the range, it's just v naught x times t. first you want to find the time that it's in the air, and then find the range. This is a little bit different from the previous problem, because now instead of having the full range of motion, we just have the second half of the motion. It's like when I wrote this question, I used a G of 9.8, so your answer might be like 1 decimal place off, or one unit in the decimal place off. Remember when you're finding your time, we're just really thinking about the y motion. We're really just working this problem. We have an object that initially has a velocity in the y direction that's equal to what? What's the velocity in the y direction of this object initially? What's the y component of the initial velocity? It's 0, right? So initially, the y component is equal to 0, and we're just dropping it a certain distance. And we want to know how long does it take to drop. So that's really the first question that we're asking. I have this object. I'm dropping it from a certain height with an initial velocity of 0. I want to know how long does it take to drop to the ground, to drop, in this case, a distance of 1 meter. And then I want to find the range. 30 more seconds or so, okay? I'll wrap this up. Stop at 4:35. If you're not sure, just ask your neighbor what they put, or maybe ask them anyway, just to test what your answer was. 4:35. Just guess if you don't know. 4:35. All right, we're a little bit over around the board here, but B is the right answer. But speed is also something you need to do. So on a test, you need to be able to work a problem like this in about 2 minutes. So remember that as you're going through old test questions and stuff, that on a problem like this where it's fairly straightforward, that you can do it sort of without really thinking about it, right? Like that guy playing racquetball, doesn't really think about it, right? He just does it. So with practice, that'll come, but it will take some practice for you. Um, so let's see, our V naught is equal to 0 here. So if I want to find that time, I just say y is equal to V naught y times t plus 1/2 ay t squared. This term goes completely away. Y is equal to -1. Remember, our y naught is equal to 0. So y is equal to a negative value. That's equal to 1/2 of -10 times t squared. So that's 1/5. T is equal to the square root of 1/5. I think I got 0.4 something, right? What was it? 0.45 seconds. So that's my time. And then if I want to know the range, x is just equal to v naught x times t. But this is my v naught x, the 5 meters per second, because it was all in the x direction. I know that in the problem because, well, it didn't say here, but it's fired horizontally times 0.45, and that was 2.3. Actually, it wasn't 2.3, it was, yeah, it was 2.3. I guess that was right. It depends how you carry your sig figs. You can get like 2.2 or 2.4. All right, that was pretty straightforward. A good basic projectile motion problem. Certainly you'll need to know how to work it for the test, but again, on the test, you'll see some slightly more complicated ones, which we'll probably get to next time. Sydney? Right, -1 is my y displacement. It's not a huge deal. Like if you put +1 there, if instead you put a +1 here, but then if you tried to do this, a square root of a negative number, you'll get an error in your calculator. So if that ever happens, just go back and think about what are your negatives and did I do the signs of the various vectors correctly? I mean, I say it's not a huge deal. It is a big deal to get that negative wrong because the answer won't work out right, but you'll probably get a sign that it is incorrect when you try to do it in your calculator because it's an imaginary number. All right, let's see. So if I drop a package from a plane, I'll show you a clip here in just a second, but if I drop a package from a plane, which of these paths will the package take? So what I'm doing here is I have a plane that's traveling along with a certain velocity, and I drop a package at this point. I don't know which path will it take. Will it fall back like that, down like that, in a straight line path, in a path that's like this, or will it travel along and then fall straight down? Which of those paths will it take? We're assuming no air resistance here, which is a fairly safe assumption for a lot of things. All right, I'll stop at 40 seconds. 40. Okay, D is the right answer. Listen, we'll see these sorts of questions come up again, but if you have a plane that's traveling in this direction, when you drop the package, that package will have the same velocity as the plane in the x direction. So this plane has a certain velocity in the x direction. The package has that same velocity in the x direction because they're traveling along together, right? And so when you let that thing go, it's going to continue going in the x direction like that. And in fact, at any point, when the plane is at this location, the package will be at this location. When the plane is here, the package will be here. And when the package finally does hit the ground, the plane will be right over it. Have you ever dropped something from a plane, like a bomb or something like that? If you ever get to do that, just watch. You can watch down and you can see that it falls right along your path. Um, I think this clip shows this. I forget. I haven't watched this in a while, but I had this X-15, which was pretty cool, and you could see where the plane would drop the X-15 spy plane, and then they would travel along the same plane, or along the same x-axis, y-axis rather. Um, well, let's watch this instead. This is from Pearl Harbor when they're bombing Pearl Harbor, and you can see the bombs. And actually, in this one, the plane drops it, and instead of following a path, it just sort of drops vertically downward. Now, these bombs actually are not just passive bombs, but they have an active guidance system, so they actually have a propeller on them. But the idea is sort of still the same. Let's do a few. Is it 8-6? It's 8-6. We get out at 8:25, right? Oh no, we're not done. We're going to do a few concept test questions. We'll come back to this question and we'll work through this. And then let's see how, next time, what do we have? And then next time, I'm going to send out those supplemental problems next time. And we'll also look at some old test questions. And we'll look at a question that we skipped back in chapter 2 because it was actually a two-dimensional question, but it comes important now. So next time, we'll largely spend more time on questions and finishing up the concept test. So let's do this now. We'll go through the concept test. We did all this stuff on vectors. So I have a small cart rolling at constant velocity on a flat track. It fires the ball straight up into the air as it moves. After it is fired, what happens to the ball? So I have this cart. It's traveling with a constant velocity in that direction. It fires a ball up with a certain velocity in the y direction. And I want to know what's going to happen to the ball after it's fired. Is it depend on how fast the cart is moving? Does it fall behind the cart, in front of the cart, back into the cart, or does it just remain at rest? We'll stop at 55, 55. Okay, awesome. D is the right answer. It's going to fall right back into the cart. Like if I have something and I'm moving along at a constant velocity, and I throw it up, it continues traveling in that x direction. It just goes up and then it follows back down. So from your perspective, this thing, I throw it up here and then it follows this path. From my perspective, I'm just sort of throwing it up and then back down again. But from your perspective, it follows this projectile path. So in this case, this object is going to travel like this, and when it gets over here, the cart will have met it. In fact, at every point, the cart will be right underneath it. Now the cart is being moved along a horizontal track by an external force. That means it's accelerating. So now, instead of moving with a constant velocity, I have it accelerating, but I still throw this ball up with some velocity in the y direction. And it's accelerating now in the x direction. What's going to happen to the ball? I'll stop at 45, 45. We're going to 48. Just guess if you don't know. 48. All right, very good. B is the right answer. Let's see. Did I tell you the pterodactyl joke? I did. What is the name of a one-legged lady? Eileen. I haven't told you that one, have I? Okay. Falls behind the cart. So if I'm speeding up, I throw it up, and then it goes behind me. You get the idea. Uh, you drop a package from a plane flying at a constant speed in a straight line. The package will do which of these? Stop at 35, y'all? 35? Okay, awesome. B is the right answer. Where does a one-legged lady work? IHOP, right. From the same height and the same time, one ball is dropped and the other ball is fired horizontally. Which one will hit the ground first? I drop one ball, it just goes straight down. Another ball, I give a velocity in this direction. It's of course going to follow a path like that. Which one of those will hit the ground first? Let's stop at 45, 45. Okay. C is the right answer. It does seem like A should be the right answer because it's traveling a further distance. But remember, what determines the amount of time that an object is in the air? The X or the Y motion, or some combination. The Y motion determines the time that an object's in the air. So if I drop something and I throw something, I drop them both from the same height. Even though this one, I'm going to give some X velocity, they're both going to hit at the same time. You can hear this better than you can see it, but you'll just listen. You'll hear them hit at the same time. Yeah, so that's because they both fall the same y distance, and it takes the same amount of time for them to fall that y distance, regardless of the distance that they cover in the x direction. That's irrelevant to the problem. In the previous problem, which ball has the greater velocity at ground level? The dropped, the fired, neither. They both have the same velocity, or does it depend how hard the ball was thrown? I'll stop at 38, 38. Okay, the fired ball. So that's the right answer. Uh, if I drop this one, it falls this distance. At the bottom, it has a velocity vy. If I have this ball, it travels this distance. At the bottom, it also has a velocity vy, but it also has a velocity vx. And the combination of those two vectors will give it a greater speed or a greater velocity than the one that you just dropped. All right. Let's see. We will pick up with this one next time. We'll finish these up. I'll have another question. Don't put your clickers away. Listen, we're putting, you can put your books away, but not your clicker. We're putting together this MCAT class. I don't know how many of you all are pre-med. You just raise your hand for pre-med? Okay, so of you, 4 or 5 people, we're putting together this MCAT class. It would cover the physical sciences portion of the NCAT. That includes physics, chemistry, and organic chemistry, which is only a small portion of the MCAT because there's also biology and psychology, and then the verbal or whatever they call critical analysis or whatever they call it. So we would just cover that one portion of the MCAT, but it'll meet in the spring, probably twice a week in the afternoon or early evening. It'll be a non-credit class. That means pass, fail. You either get an S or a U. If you come, you'll get an S. We'll give practice tests. We'll cover all the material. It's a really fast course because we're going to cover all of physics, all of chemistry, and all of organic chemistry during that semester. But it's meant to be sort of like the Kaplan course, except only covering the MCAT, only covering the physical sciences portion. So if you'd be interested in that, please click in A, yes, B, no, or C, maybe, like if you are pre-med. All right, y'all have a great day. Remember, if you're pre-med especially, please answer this.